All right, so our intro information is that sampling distribution is a distribution of a statistic. It's a probability distribution. It's made up of means or proportions or chi-square or a number of different things. Today we're dealing with means and proportions. This is going to be taken by the statistic x bar or p hat in all possible samples of the same size from the same population. So it's not like standard normal calculations where we're interested in where individuals fall in a distribution. This is where sample averages or sample proportions from samples of a given size show up in relation to all possible samples of that same size. Okay? So, and we're going to get some probability answers from it. So we're going to be referring to the sampling distributions of x bar for means or p hat for proportions. So starting out with proportions, all right, the sampling distribution of p hat is close to normal provided that we meet certain conditions. And the mean of the sampling distribution of p hat is the parameter p. Okay, so if we can get all possible samples of a given size and they're all drawn without bias, the center is going to be our parameter p. That's how we know these unknown values, through repeated sampling. All right, so mu of p hat equals p. The standard deviation of your sampling distribution is sigma of p hat equals the square root of p times 1 minus p over n. P is something we aren't supposed to know, but usually in problems of this nature we're given it. When we do inference, we usually replace the parameter p with p hat. All right, so going back here, if this n increases, that means you're going to get more accuracy. This will get smaller as a whole, and so your spread will get tighter. So larger sample sizes are more accurate. Standard deviation decreases as n increases. So to cut your standard deviation in half, you quadruple your sample size. You may remember that. All right, these are the conditions that we need to use these formulas. So we only use that standard deviation formula of p hat when the population is at least 10 times the sample size. So there is the origin of your 10% rule. And we can only claim normality or state that we're in an approximately normal environment for your sampling distribution for p hat when n times p is greater than or equal to 10 and n times 1 minus p is also greater than or equal to 10. These give you an adequate sample size to make your sampling distribution nearly normal. All right. These became assumptions for inference and for estimation, for confidence intervals, and for z-tests for proportions. All right, for means then. Now we'll move on to that. So suppose that x bar is the mean of a simple random sample of size n drawn from a large population and having a mean mu and a standard deviation of sigma. All right, the mean of your sampling distribution, the dead middle, well, not so much the dead middle of it, but the average for all possible samples of a given size of all those x bar values is the true value for the population, and its standard deviation is sigma divided by the square root of n. All right, and this will have the same kind of general behavior as the standard deviation for proportions did. So as n gets bigger, the whole fraction gets smaller and bigger sample sizes are more accurate. So your sample mean x bar is an unbiased estimator of the population mean mu. Your values of x bar are less spread out for larger samples. That's because of that feature that I just talked to you about on the previous slide. Your standard deviation decreases at a rate of square root of n, so you have to take a sample 4 times as large to cut your standard deviation in half. I believe that was the same that we had for proportions. All right, and your population has to be 10 times the sample size in order for that formula sigma divided by radical n to be valid. Now these rules do apply no matter what shape the population has. We are interested in shapes that are bell curves, normal. That's what we're looking for. That's why we have the central limit theorem. So if a sample of size n is large enough, a population with mean, mu, and standard deviation sigma will give you a sampling distribution of means, x bar values, which is approximately normal. And this is true no matter the shape of the population distribution. I'm going to show you that here in a moment. So, how big should n be? If it's greater than or equal to 30, then your central limit theorem applies. So, you just have to indicate that you're in a central limit theorem condition by indicating that your sample sizes should be greater than or equal to 30, or that you can name how big it is, provided that it is over 30. You just have to make sure people know it, especially the people that read your AP answers for your AP exam. Okay, so this is what I wanted to show you, and we have seen this before. See how nice and normally distributed the population here is? It's perfect, okay? I'm going to go and show you what it looks like to get a sampling distribution, at least an approximation of one for samples of size 2. And I could even animate it, so I could drop these all down and average, average, average. That's pretty boring. But if I do 10,000 or 100,000, all right, it looks pretty good. But wow, this isn't working out quite the way I'd expected it to work. Oh, I'm sorry, of course it works good. The reason that it works good, duh, is because if your population is normal, your sampling distribution, no matter how big your sample sizes happen to be, will also be normal. So if I'm doing it for size 5, normal, of course it's skinnier because less error. If I'm doing it for size 10, approximately normal. I'm doing it for size 20, approximately normal, right? So if your population is normal, then any sampling distribution is going to be normal. You don't have to worry about your central limit theorem for sample size. Okay, sorry about this. I just had a little bit of a brain freeze. All right, so let's look at one that's skewed. All right, if I go back to a sample of size 2, it's too slow. All right, that's going to be skewed. That's going to be skewed. All right. If I want to go to a sample of size 5, that's still skewed. All right, less so, but it's still skewed. All right. If I want to go to a sample of size 25, which is close to 30. All right, that's nearly normal. There's your central limit theorem at work. Big enough sample sizes, doesn't matter what your population looks like, you're going to get something that's nearly normal to do normal calculations on. Okay, so I'm going to just make one up that's terrible, right? So here's one that is bimodal. Okay, now if I just do samples of size 2, here's what's going to happen. I can get one from here and one from here and get an average. I can get one, let's just maybe change this, maybe get one in the middle, so that would look, that would show up here, and then you can get one here and one here, that would put you a little over here, one here and one here, that would put you over here. You get 2 in the middle, or you could get one here, and that would drop it in the middle. So you should get like 3 peaks. See that? That's what happens when you're only averaging 2 things. Now, if you start averaging like 5 things, right, it still gives you 2 peaks, but it's getting a little bit better. Right? If I go up to 25, even as weird as this looks, go ahead and there you go. All right? It's because you're taking so many individual values from this entire distribution that they're all averaging close to the center or nearly close to the center. So there's your central limit theorem at work. Okay? All right, last thing then that I want to do, and let me pause for just a second. All right, I'm back. Sorry about that. All right, I want to just work. This is the first problem from your assignment. And after that, I'm just going to have you do 2 or 3 other ones. Most of them are means, sampling distributions for means. Definitely just, make sure that you're aware of conditions should you run into something with proportions, because if you don't meet those n times p and n times 1 minus p requirements, that could mean that you would be doing a bunch of calculations that you really shouldn't do. All right, so starting out with this first one, weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount that the packaging machine puts into these bags is believed to have a normal distribution, so we'll just call this normal, with a mean of 10.2 and a standard deviation of 0.12 ounces. All right, so they're clearly advertising below what they're planning to put in these bags, I guess, to hold off on possible lawsuits for false advertising or whatever. So what fraction of all bags sold are underweight? All right, that's just a standard normal calculation because you're looking at all bags singly. All right, anything stating 10 ounces, anything below that, since they stated 10 ounces, would be underweight. So we're looking at the probability that X is less than 10. All right, I didn't put an X bar because we're not in a sampling distribution. So if you're so inclined, we can draw this out for our reader, and we can center this at 10.2, and we're looking at anything at 10 or less. So we're looking at this. So this will be the probability that Z is less than, remember, Z, we're just dealing with this X minus mu over sigma. All right, so this will be 10 minus 10.2 divided by 0.12. All right, and this is going from negative infinity up to 10. So I'm not going to go ahead and convert this to a z-score. I'm just going to use, since I've defined the random variable and I drew a picture and I wrote it out with the standardizing, I can go ahead and do the normal CDF. So normal CDF, and I'm going from negative infinity, so just negative 1,000 or whatever, up to 10 with a mean of 10.2 and a standard deviation of 0.12, and that will give me 0.0478. Okay, so there's the first one answered. And then it says some of the ships are sold in bargain packs of 3, which sounds like a sample, but it says what is the probability that none of the 3 is underweight? All right. Now that's sort of a basic probability question. So this is just the probability that none of them are underweight. All right. All right, well, we know what is the probability that they're underweight, and that's 0.0478, but they said the probability that none of them is underweight. So that should be 1 minus 0.0478 for any individual bag not being underweight. So that's 0.9522. So the probability that none of the 3 is underweight, so that's the probability of the first is not, and the second is not, and, see, the and means multiply, right? The third is not. So basically, that's just going to be 0.9522 times itself 3 times, or raised to the third power, which is 0.8633. All right, so that's not really any kind of a normal calculation. That's just kind of basic probability. So let's see what we have here for number 3. what is the probability that the average weight, so an average would be X bar, of the 3 bags is underweight? All right? So let's go ahead and set this up. So here n is going to be 3. And since the population is normal, your sampling distribution is also normal. It should be centered at mu, so 10.2. But you will change your standard deviation into standard error. So that'll be 0.12 divided by the square root of 3. Okay? So now when we do this, this is going to be the probability that X bar is less than 10. All right? So this is the probability that Z is less than, all right, 10 minus 10.2 divided by 0.12 over square root of 3. All right, that's where things sort of are different, okay? Now, I don't really feel I need the curve since it's sort of the same as this. I did write out the sampling distribution parameters. So I'm just going to go ahead and do normal, CDF. It's still going to be from negative 1,000 up to 10. And the mean is 10.2. And the standard deviation will be 0.12 over square root of 3. Now you can get an approximation for this, or you can just put this in your calculator exactly the way it's written. And it should be a lot smaller than the average of the probability of seeing an average of an individual bag being underweight, since it's relatively rare that one bag is underweight. It's only 5% of the time. An average for 3 should be rarer still. All right, so this should be 0.0019. All right, and now the last one is, what is the probability that the average weight of a 24 bag case, okay, so average again is X bar, n equals 24. So this is an even bigger sample size. All right, so here we go. Probability again that X bar is less than 10. All right, oh, by the way, this is normal, with a mean of 10.2 and a standard deviation of 0.12 adjusted by the square root of 24. All right, so probability that Z is less than 10 minus 10.2 divided by 0.12 over square root 24. Get that to draw for me. And that's going to just be another normal CDF, since I've already gone ahead and defined my random variable and shown the Z calculation. So this is normal CDF. Again, negative 1,000 because it's less than. It's going to negative infinity up to 10. And the mean is 10.2 and the standard error is 0.12 over square root 24. And that is essentially 0. See how small this is? Well, if you ramp the sample size up from 3 to 24, you should never see the average for all 24 bags being underweight. That should practically never happen. The number is something times 10 to the negative something huge, and so that's a completely expected answer. So go ahead and do that assignment for review of sampling distributions. And on that note, I will bid you a fond farewell.